Okay, so we're in chapter 8, memory management. This is also a big chapter and more complicated than the other things. Okay, so let's start. We're talking about memory management.
Wait, you have to record.
I am?
You aren't recording.
Yes, I am.
You are?
Is it that there?
Oh, okay, I see it.
Background. So what is memory management? Somebody want to tell me what their guess would be?
How it manages the memory?
Like how it allocates memory?
Yeah, how it allocates memory. Allocates memory between what?
Processes.
Between processes, right, exactly. In other words, one of the jobs of the operating system, one of the main jobs of the operating system is to make sure that the memory used by one process is not interfering with the memory used by another. There's a separation, we call that protection. Right, it's protected, the memory is protected between the different processes. What's another thing? Well, I always like to imagine how you, imagine what you learned in Mips, you know, how you programmed in Mips, and then how you program it, and then imagine two programs running. When you ran in Mips, you, let's say, use some memory location, let's say, the beginning of the memories section, and the memory of the beginning of the data section of memory. Now you may have two, so that was fine, you could access that. But what if there were two programs running on your computer, and they both are saying, I want to access memory location, the beginning of the data section? Well, how would that work? You see the problem? In other words, in Mips, you said, I want to go to memory, you know, you made an array, and it gave you an actual location, like, and that location was going to always be, remember, was it 10 million, 10,000, right? That's where it was every time, because that's the beginning of the data section. So if you had two programs running on a computer in a shared system, you know, with time sharing, then who's going to get that location, 10 million, 10,000? They can't both get it. They're going to write on top of each other. Do you see the problem? That's just a problem of, that's a problem of like, wait, does everyone understand the problem? Somebody understand the problem?
Not fully.
In other words, when you wrote a program in Mips, where would you put your array? At what location? Do you remember the number?
In the data.
In the data section. But where did the data section begin?
It was lower down.
Yeah.
It wasn't,
Yeah, since we have a computer here, let's
blinking on which one it is.
Oh, actually, okay. Well, there. Mips memory diagram. Yeah, here. Remember this picture?
Yeah.
Here, actually, it has the number 400,000. If it doesn't have the data segment, I would like a picture with the data segment number. Yeah, here. Here's a better one. Can you see that? It says 10 million. The data section size is 10 million. When you make an array, it's going to go at location 10 million. But if I have two programs running simultaneously, this is what we're talking about, two processes running simultaneously, and they both have an array, and they're both at location 10 million, well, that's impossible. That's going to be a problem, right? So how are we going to solve that problem?
Virtual memory.
So we're going to use something called virtual memory, or even before virtual memory, we're going to use something called, we're going to differentiate between physical memory and logical memory, or a physical address and a logical address. In other words, the logical address for both programs will be 10 million, but the physical address will be different. And that will allow the two people to think, will trick the programs. They'll think they're both running at 10 million, at location 10 million, but really one is and one isn't, or neither one are, could be.
Nothing's really simultaneous.
But it doesn't matter, even if it's time sharing. So there's two programs, one's running and the other, run and the other.
So
I
one
don't,
is
but
gonna
still,
get
I don't
to
want to.
first.
Yeah, but one's got an array over here, which has the two dots of hoods of 1,000 students, and the other's got an array over here of the birth dates of 100 teachers. So they can't, if they're both on the same location, what are you gonna do? Copy them out and move them back?
No, They're not on the same location because
Exactly.
by the time the second one gets there, the spot's already taken. I guess you could write over.
Yeah, but okay, so this is the thing, when you guys are used to writing your program, you guys are used to writing your program in Mips, like you just write my array, and you just put it in the data section, and then but actually when the assembler compiles it, or assembles it, it puts a number there. It doesn't actually put my array. It actually figures out where to put it. And where does it figure out to put it? Not based on other processes. It doesn't know anything about other processes. The assembler is just always going to choose the same number. It's always going to choose 10 million for your.
So then it's like writing.
So
over.
then it'll write over it. It doesn't know, the assembler doesn't know there's other processes there. So basically that is our main topic now, is different ways to deal with that. Deal with having different processes using, we want to give them the look and feel of having the whole computer at their disposal, when really they're only getting a small section of the computer. Yeah.
In the last homework, when we had the acquire, like in release, and like we wanted to access the stack, like there was push and pop, and then we just locked one out of the other.
Yeah.
Could we do something like that, or not?
You could, yeah. I mean, you're saying, yeah, but then we had to have another place to put it. The push and pop there was not arrays. The push and pop there was registers, values in the registers. We put them into memory. Now we're talking about the memory itself, because that was where we were talking about the registers. We want to reuse the register between different people, so we put them into the memory. So we could, if we had like some extra memory, we could move the memory into some other memory place. But here we don't have any extra memory. We're already at the end. We're at the memory. We can't go any further than that. So no, it won't. I mean, I understand what you're saying. Conceptually, yes, you could put both people in the same place and then just take them out and put them there. But it could be that the array is very big. It could be an array of 10 million students' IDs. I don't want to start copying all that information somewhere. When we were doing it before with the push and pop, we were just putting a few registers, right? Maximum 32 registers. Here we could have millions of data points. We don't want to move those. So that's not a solution. Okay, so programs must be brought. Okay, so now this is just background. Programs, this is you should know, programs must be brought from the disk into memory and placed within a process for it to be run. In other words, if I want to run a program, I got to take it from the disk, put it in memory, give it all the process information that's in the PCB, give it all the accounting stuff, and start it. Main memory and registers are only storage CPU can access directly. The CPU can't access directly the disk. It can only access the registers and main memory, and that's why the program has to be in main memory. If we can't run programs off the disk, right? Of course, nowadays we do sometimes run an operating system off of like a disk on key, a flash drive, which is a kind of, it's not really a disk, it's a kind of memory. So in between. Memory unit only sees a stream of addresses, read requests, or addresses and data and write requests. In other words, we just have an address and we write to that address or read from that address. All right, we can skip this. Cache sits between the main memory and the CPU registers. All right, I'll skip the rest of this. Okay, so here's that same picture. Remember we saw that same picture? That same picture I just showed you with Mips. Now this is similar because we're taking that same memory from, here we drew it backwards though, from 0 at the top. The other one was 0 at the bottom. Doesn't matter. And here, let's go back to that picture. This picture, remember, had 0 at the bottom here. And reserved, what does it mean reserved? Memory for the operating system. So here's the operating system. And then we had text and data and the stack and all this stuff. All these sections, that's all the things that the program needs. All of those are going to fit into this section now. You see what I mean? Into the one section for one process. Each process will have his own text section, his own data section, his own stack. As opposed to having the entire memory at his disposal. That's the way we did in Mips, right? In Mips, we had the whole memory. We were like rich. We had the whole computer to ourselves. Here, we are going to say the whole process, all of his stuff has to be in this section. This is process 1, process 2, process 3. And this is maybe unused. So what does that mean? That means that we're going to have what's called a base and a limit register, which means, let's go back to the picture. Here. This is actually very good that you guys are remembering your MIPS and that I taught it to you so that we're all on the same page. But this, what did I teach you? I taught you the lab?
Yeah, the
Just the lab. So, okay, back again. So what's going to happen is, let's say here is 0. From the perspective of this process, this 400,000 is actually here. And I mean, it's upside down. It's a little bit annoying with this picture. They drew it this way. But this is his 400,000. Then his data section will be somewhere over here, you know, and his stack will be over here. So all these sections are cut up inside here. So that means this 2,000, what is this, 256,000, this number actually will be 0 or 400,000. Let's think of it as 0, the beginning of his main memory. So from his perspective, when he says write to location 0, when the program says, from my perspective, I don't know anything about any other programs. I have no idea where I'm sitting in memory, but I want my array at place 0 at the beginning. So the operating system is going to put it here at 256,000. And when I say, give me the value at array location 0 plus 4 or 0 plus 8, he's going to give me not 0 plus 4 or 0 plus 8, he's going to give me 256,000 plus 4 plus 8. But I don't know that. I'm Mr. Process. And I just say, give me 4, give me 16, give me whatever I want. And he's going to add that number to what we call this base register. That's what's in blue over here. That's the base register. That is my starting point. What is my actual starting point? And that's not my job, that's the operating system's job. And then I also have a limit register, which is saying, if I try to go outside, let's say I try to say, from 0, I want to go to now to 10 million or whatever. So it could be that 10 million is beyond the range that I'm allowed. And I'm given a certain section, and that's it. And that's my limit register. Now the truth is, what determines that limit register? Well, the operating system just gives everybody, is it communism? Everybody gets the same piece no matter what? So the answer, so can somebody guess what the answer is going to be? It's not, well, it's not going to be like that. It's not going to be that everybody is going to get the same. What will it be? Imagine, I'll give you a hint. Imagine the program has no, your C++ program has no new operation. You never do new in your program. Everything is static. All your arrays are static. So what's going to determine my base and my limit register?
Where the first array is put, and then would be the base, and then after that is just whatever limit the memory has, they'll just keep filling it up until then.
Right. At compile time, at compile time, we know exactly how many arrays are going to be. There's no news in this program, right? We know exactly how big the program is going to be. We know how much memory, how many arrays, but it's, by the way, it's not just arrays. What else is it? Yes, it's also variables. What else is it?
Yeah, anything.
Well, okay, linked list, yeah, yes, right. Well, linked lists are usually dynamic, but yeah, I'm talking about just static. Imagine we just have static. But functions, but yeah, functions. Well, every function. What does it mean, functions? The code of your program. The actual code. Remember, there's a code. Back to the picture. Look what's written here. Data, but what's written here? Text. What's text? That's the actual program. So if you have a program that's 1,000,000 lines long, that's 1,000,000, pieces of data that you're going to have to store. So your program, but the point is at compile time, I know exactly how many arrays, how big they are. I know exactly how many lines of code my program is. I know the size of my program. So I can determine the base and limit register immediately. Yeah? I know that. It's determinable. So it could either be fixed. I mean, it could be communism. It could be fixed. but it could also be variable, and it could be dependent on the actual program. CPU must check every memory access generated in the user mode to be sure it is between the base and the limit register for that user. That's protection. In other words, I can't access, the operating system has to make sure that I don't go to other locations. Everybody should be with me. I see people on their phones. It's not a good idea. Not a good idea. You can be on your phones all the time. I know it's, you know.
Sorry, my boss
When you're,
is in
I
a
know when
Velas
you're
and
driving,
No, my
it's hard to not look at your phone.
my boss is in a Velas
When
and
you're
running our
operating
store.
farm equipment, it's hard to not look at your phone. But
No, I
in
understand.
class, don't look at your phone.
My boss is in a Velas and I'm running our store and it just
Doesn't matter.
So no, I had to
Tell
send
her,
him
write her a
something.
message that you're busy right now. Hardware address protection. So how are we going to do this? So, I mean, this is just showing you kind of what we just said. We have a base we have a base register, which is where we're starting from. The limit here is an important point to understand. The limit is not the absolute number. In other words, the limit is not 300,040. The limit is the range, the size. In other words, it's that plus, how much more I have. The limit is, you see what I mean? The base is where I actually start, the absolute address. The limit is how much I add to it. You see, look what he wrote here. Look at the limit is here. It's actually a very good picture. He wrote 120,000. Why did he write 120,000? Because 120,000 plus 300,000 is 420,000. You see? The limit, it's a little bit confusing. The base register is where I actually start from. Where in the world am I actually starting? Where in the memory am I starting from? The limit is how much, what's the range? What's the range here? The range is 120,000 and 900. The actual size. The limit is not like where it's not the end point. You see what I'm saying? The limit is not the end point. It's how big is it? It's like saying your house starts at this location and it's 100 meters long. It's not saying your house starts at this location and ends at this location. This is not a location. This is how much I have to add to the base to get. So therefore, this is going to make sense here. The address that the CPU wants to, let's say I'm running a certain process, and the CPU says, according to your code, it says, go to address space X. If that address, it's going to take that address space, it's going to check and make sure that that address is, it's going to add the base to it. Sorry, what does this mean? If the address is greater than the base, then that's good. And if it's less than the base with the limit, then that's also good. Then it'll go there. But if the address that I got is, the address that I got is too small, it's not greater than the base, it's too small, then I'm going to say you can't access that. It's beneath your base. And if it's here too large, it's going to say it's not accessible. Now, what is the CPU? There's one thing missing in this picture, which confused me for a second, which is that the CPU doesn't actually, how does it create that address? In order to create the address, it has to actually add the base register to it, right? What I just said is, if I say go to place 0, it doesn't really mean 0. It means 0 plus the base register. So who's doing that job of adding the base register to the address the CPU normally computes? So it's something, it's something that we're going to see. It's something called here. It's called this, MMU, not MMY, MMU. Memory Management Unit. There's a piece of hardware called the MMU, which is very important in this chapter. It's a very important thing to understand. It basically does a very simple job. It just adds the base register to every address that the CPU creates. So in this picture, we're ignoring it. But essentially, in between the CPU and this, on this arrow is the MMU, which is adding the base register to the address. You understand this point? In other words, the CPU says, go to address the beginning, the first address, 0. But that's wrong. I don't want 0. I want 0 plus whatever is my location.
What were you saying about if the address is beneath the base, then it's not accessible?
Well, I'm just explaining what this diagram means. If you understand the diagram, then you're okay. this diagram is just saying, if the address is greater than the base,
Then it can continue.
then it's good. You go, if not, then track to operating system monitor addressing error. In other words, you could have a pointer in your program that says go, like I could make my whole program and then I could have a pointer that says go to location, 10,000. I can do anything with what I want with a pointer. And then the operating system will say that that's not in your range. Right? That's why your programs crash when you screw up with the numbers. If you put the wrong data, if you forget somebody's a pointer, you put the whatever. If you manipulate your pointers the wrong way, your program can crash. What does it mean crash? The operating system crashes it. The operating system says, I'm not letting you get to that memory location. And then you crash.
So whenever it has no, that means it's gonna crash?
Yeah. Programs on disk, ready to be brought into memory to execute, form an input queue. Okay. Without support, must be loaded into address 0. This is what I was just saying, right? Everybody wants to be at location 0. All the programs think they're the only ones around. Why should they know about anybody else? Inconvenient to have first user process physically addressed always at 0. But how can it not be? Right? This is what I was explaining. Everybody thinks they're at 0. Further, address is represented in different ways in different stages of a program's life. Right. Source code addresses are usually symbolic, compiled code. In other words, what does it mean source code? When I write in my source code, I say like int a, and then I say a equals 50, and then I say a plus plus. So when I say a plus plus, that's a symbolic representation of an address. It's not a number. That's not like in Mips. In Mips, I wouldn't say that. In Mips, I would say go to address number 110 and add to it. But in source code, it's symbolic.
I'm confused. Source code.
In a high level language, you refer to memory by a symbolic name, by a name. Symbolic just means by a name.
So you don't want its actual address. You want the-
No, we're just now describing the difference between how you program and how it actually exists on the computer. When you program with letter names of variables, but they don't obviously exist that way on the computer. There has to be, therefore, something called address binding. And that's what actually, yes, unfortunately, I didn't, I edited these slides and I don't have the edited version. I'll upload the edited versions, but no, I can't do it now. I forgot my computer. So anyway, the point is that there's something called address binding. And it's a very important thing. You can, I don't know if it has, yeah, for the next slide, we'll talk about it more. But first, we're just expressing the problem. The problem is, or the issue, what's going on? I refer to it as symbolically. Then I compile it. I could refer to it as I could refer to a particular variable as 14 bytes from the beginning of this module. In other words, my variable, just like an array, if you think about it, I don't know if I ever told you this when we did Mips, but every variable in a high level language, like I say, int a equals 5. What is that a? In Mips, we just had arrays and registers. So what's int a? What do you think? Right, in Mips, we just had arrays, and we declared arrays, and then we had a register that you could use. So what's int a?
It's you're allocating a number of bytes to store some data.
So right, exactly. So therefore, what is it more like, a register or an array?
Register. No, an array, because
It's more like an array. Essentially, an int. If I say int a, it's an array. It's an array of one element. If I say int counter, that's an array called. And that's just how I give it a name. It's essentially an array. So I'll have lots of arrays. So those arrays, where are they? At the beginning of the memory. So one could be 14 bytes in the beginning of the memory. One could be 30 bytes in the beginning. Essentially, those are the locations. But eventually, it needs to go to an actual physical location, not just 14 bytes from the beginning, but actually address space 3,253. I don't care beginning of location. At a certain point, it's going to be the actual location. So the linker or loader will bind relocatable addresses. Notice 14 is relocatable because I could theoretically move it to any segment here. If we call these call these segments, process. Right? I could put my program in any one of them and it would work. But eventually it has to be bound directly to an actual number, 420,940. It has to be actually there.
So bounding is when it actually puts it where it is in the memory rather than like right in the beginning?
Yes. Address binding is putting the address in its actual physical location and not just a theoretical. And we're saying there's 3 stages before. First, there's symbolic, where I just have it in my mind or in the program in high level language. And then there's from the beginning of the module, that's like in Mips, that's how I would do it, right? But then there's actually putting it somewhere. Each binding maps one address space to another. In other words, from the variable to the physical. So this is also an important point. When do we do this address binding? Address binding of instructions and data to memory can happen at 3 different stages. Now, again, what is address binding? Address binding is saying, take your relative address and make it an absolute address. You understand what the difference between relative and absolute? Absolute means where it absolutely is. Relative is like, okay, from the beginning. When does this happen? So it could happen at compile time. And that's actually the most easy to understand. I compile it, and somehow the compiler says, you're going to go in section 10. You're going to go in section 4. And the compiler just puts it all. That's not the way it really happens, but that could happen like that, right? That would be that way early computers would be like that. If memory location is known a priori, in other words, I know it from the get-go, then absolute code can be generated. What do I mean by absolute code? The code, I actually create assembly code, which has in it the exact addresses that I want. You see what I mean? In the assembly code, it says go to memory space 3000. But that's only if I somehow know where I'm going to end up sitting.
What's absolute code?
Where the code has in it the actual addresses that I want to be sitting at. But what's the problem with that? Must recompile the code if starting from location changes. Now, there's all of a sudden I want to put this program on a different computer, or I want to run it again. It could be I'm in a different place now. So I get to recompile the whole thing because the compiler, I bound it at compile time. Everyone understands that point? If I bind it at compile time, when I compiled the program, I said I'm going to be in location 10 million. So that's it. I can only run the program if I'm at 10 million. I can never move. If I want to move, I have to recompile. So that's why, so nobody does it that way anymore. That's not the way your programs are going to be done, even though that's like the most simple and straightforward way to do it. The next thing is load. Well, actually, let's skip. Load time. What is load? Must generate relocatable code if memory location is not known at compile time. So load time would be like I compiled the program. Imagine this. I didn't bind it at compile time. So that means the compiled program is not going to say, do a LW, load word from this actual location. It's just going to say, do a load from, offset from the beginning. It's going to give me some kind of semi-compiled program. It's going to say from the beginning, and then at the loader will replace all the addresses. The loader, that would be load time, when I actually load the program. So now all of a sudden I can have a compiled program, it's sitting there, and it's just the job of the loader. Every time I load the program into memory, it's going to change my code so that it'll run at that new location. That would be load time. That's also kind of a weird thing. But let's talk about execution time.
But I'm a little confused with load time.
Load time means when I load the program from the disk into memory, is that the loader, he'll be his job to redefine all the addresses so that they correctly reflect where the addresses should be in the location that I've been loaded into. One time I'll load it into place 10, another time I'll load it into place 10 million. So then the addresses in the program, in the compiled version of the program, will have to change. So I'll have to go through and change all those addresses everywhere in the program. So the compiled program will be relative addresses. Okay, the third type is execution time. And this is actually the way programs run nowadays. What does it mean, execution time? Binding delayed until runtime. If the process can be moved, during execution from one memory location, I don't know why, in other words, it is moved. So the runtime means that even when I load it into memory, I still don't have an absolute address of where my loads and my store words are going to be. And I leave it as the way it was in the load time, I leave it undefined, or I leave it as 0. It's not undefined. I leave it as 0 from the beginning, 14 from the beginning, 100 from the beginning. In both load and execution time, I leave it as this, assuming that I'm at 0 every time. Assuming that I've been put into 0. I leave the addresses as, let me say this more clearly. In both load time and execution time, I leave the addresses as 0 or 14, small numbers from the beginning, assuming that I've been put into location 0 in memory, even though I know I won't be put there. But I leave it like that. I leave it as 0, and that's the compiled version. The compiled version says load word from location 8, store word to location 28, all these small numbers, as though I'm at the beginning. And in execution time, look at this little green arrow, need hardware support for address map. That's the MMU. Every time I want to go and do a load word, the special hardware called the MMU will come along and add to my address. I said 0? Oh no, it's not going to be 0. It's going to be 10 million and 0. 10 million plus 0. If you want 8, no, it's going to be 10 million plus 8. It's going to be whatever location I'm in. On every single load word and every single store word, there's going to be a operation done. I'm going to have to take that number and add to it another number and get a new address number, and that will be where I actually go. Now, what's the problem with this?
That expensive.
It's very expensive. It's slow. Expensive when you say expensive, you mean slow.
Yeah.
Exactly. I'm going to have to do an add. So that's why we need special hardware. We can't let the CPU do this. If the CPU is going to do this, the CPU is going to be wasting all its time doing these adds to every single address, every load word. So we build special hardware that is specially designed to just do this one job of adding numbers. And this hardware is essential for having, basically it's essential for having a multitasking computer. All modern computers that are multitasking have to have this hardware. And this was an innovation. We're going to have to make this hardware. And his job is to redefine every single address to the new location. So
what does MMU actually stand for?
Memory Management Unit. Here, Memory Management. We still get there though. What is this picture? Yeah, this picture we can skip really, but this just shows you. This is like the life cycle, the life of a program. The source code, then it goes to compile. This is compile time. Then it becomes an object. Then the linkage editor brings in other modules, and then it's loaded into memory. All this is load time, and then execution time, in-memory binary, memory. And then there's dynamically loaded system libraries. That's what I did. A DLL, a dynamically loaded library, is something is a library that's added at runtime instead of at compile time or load time. Anyway, this picture is not. It should be obvious to you, but if you don't understand the details of it, it's not important. Basically, just understand there are 3 stages: compile time, load time, execution time, and any one of those stages can have the final address finding occur. And like I said, it's actually going to be in execution time. That's the nowadays it's done. So based on what we just said, we have to say that when I say the load word in my, I'm going back to Mips again. When I say load word in my Mips, that address that I say 0 or 14 or 8, it's actually not the physical address that it's actually going to be running at. Is that agreed upon? It's not the actual physical address, that 8 or 3, because I don't know where I'm going to be stuck in the memory. So we're gonna come up with two terms now. One term is gonna be called the logical address and one term is the physical address. The logical address we're gonna call the way the program sees it. In other words, the program before the MMU got involved. The program thinks he's at location 0. From his perspective, that's the logical. That's the logical. In the logic of the program, that's the address. The physical address is what the hardware actually wants to, where it actually is in hardware. So it says, look here, it says logical address generated by the CPU, also referred to as a virtual address. Although I prefer logical address.
So logical
Because I
address.
think I want to reserve the word virtual for something else. But a logical address is what the CPU generates based on your code before before the MMU got involved. I mean, I'm skipping ahead. You didn't yet mention the MMU. The MMU is the next slide, but I'm saying that's the way I'm defining it. Physical address seen by memory unit. In other words, physical address is the actual address. But it's important to understand that the address that the computer thinks that it's writing to, or that the program thinks it's writing to, or the CPU thinks it's writing to, is not the address that it'll actually write to. It's going to go through an alteration. Logical and physical addresses are the same in compile time and load time address binding schemes. Somebody want to explain that sentence to me? That should be obvious. That should be a review of what we just said. But let me read that again. Logical and physical addresses are the same in compile time and load time address binding schemes.
Is that because it's like the MMU wasn't used yet?
Yeah, exactly. We're not using the MMU. In those, remember, we're talking about 3 different theoretical ways to compile a program to get the physical address. One is do it right away, it's compile time. And in that case, there's no difference between physical. In other words, we only have the concept of physical and logical addresses being different when we are talking about runtime address binding. By the way, if you know what address binding is, you're already can sound very smart in dinner conversation. Right, address binding. Does your program do compile time address binding? Because it sounds like a very fancy term. You can ask if you're going on a date with the programmers. Do you prefer compile time address binding or runtime address binding? Just want to know, it's going to affect our marriage.
So you ask your wife.
No. Okay. Logical, it's a silly question. It doesn't make any sense, in fact, that question. Logical and physical addresses differ in execution time. Wait, logical and physical addresses differ in execution time address binding scheme.
That's because
That's
MMU is
because the
here.
MMU is changing it in the middle. That's exactly what's going on. Logical address, and so now we can have another term. Now that we understand what logical and physical address, we can have another term called the logical address space and the physical address space. When we say address space, we mean the range of possible addresses. The set, or the range, of all logical addresses generated by a program. The physical is the set of all physical addresses generated by a program. When we talk, here, a little peek ahead to what we're going to do later. Why do I say that I prefer logical and physical to virtual? Because virtual I want to reserve for something else. What do I want to reserve it for? What about this? What about, imagine, if you will, a computer that has only has a gigabyte of memory, yeah? And I want to run a program that requires 2 gigabytes of memory. Could I run it?
If you do it in parts.
If I do it in parts, I could. But does that make sense? As I could bring, what does it mean in parts? I could run the first gigabyte of the program and then move it out to where? To the disk. The disk might be 8 gigabytes, so I can use the disk. I can move the program out to the disk and then move the second half of the program into memory and then run that. So I could run a 2 gigabyte program if I have only 1 gigabyte. That only works though if,
You have the disk space?
well, for sure I have to have the disk space. And what else? Is that going to, put it this way, is that going to work in compile time address binding?
No.
No, because compile time address binding would say This is memory location 1, this is 2, and this is memory location 2 billion. But there is no memory location 2 billion because I only have 1 billion places. My memory is only 1 gigabyte. I don't have to it. But once I have once I have a logical and physical, which are disparate, which are separate worlds, then I have freedom. I can say, the MMU can all of a sudden say, location 2 billion, yeah, it exists. But we're gonna put it at 0. We're gonna put it anywhere we want. So that's virtual memory. So that's why you see virtual memory is also confused with logical address space, because the logical address space can be larger than the actual physical address space. See what I'm saying? So we're talking about address space. That's why I mentioned here. Logical address space and physical address space. They do not have to be, normally we think about the logical address space as being smaller than the physical address space. The physical address space is the whole range of the computer. And the logical, like we saw in this picture, might be only this little box that I got. But it actually theoretically, and in fact will be, could be bigger than, also it could just like it could be smaller. The logical address space can be larger than the physical address space in a theoretical, in a real sense. Okay. So here we're going to define the MMU, and I already defined it for you. It's the hardware device that at runtime maps virtual to physical addresses, right? Does that sentence make sense? Questions on that sentence? That should be exactly what we just explained. Many methods possible covered in the rest of this chapter. So you hear that? Basically what that sentence says is now the rest of the chapter we're going to talk about how the MMU is going to work. You see what I mean? That's the whole topic. The whole topic is actually how are we going to do? We're talking about compile time, so that's simple. But there are many methods possible to do this runtime. You gotta have a comment here. Somebody else in the chat. Can you clarify virtual and logical, Gabrielle? I just did clarify. You still want me to clarify? Anyway, I think I spent enough time to go over it again. To start, consider simple scheme where the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. Right. All of a sudden, we're talking about a relocation register. We never even, did he mention it before? No, he didn't, but, okay, here's a picture. Yeah, here, look at this picture. We'll go back, but here. You see, here's the MMU. Just to let's talk a little bit how the MMU is going to work. You see the picture there? Is it in focus? Doesn't look like it's in focus to me, but whatever. The MMU is doing this plus. See that plus symbol?
You can make it a full screen.
I can make it a full screen.
You can do slide.
Yeah. View.
No, you can go to slideshow.
And presentation.
Slideshow on top, right next to review, and then you can do present. Current slide.
Okay, thank you. I should have done that before, but nobody complained. So the plus means that that's essentially what the MMU is doing. Because remember, I said my logical addresses are usually small numbers because they're like from the beginning. Where else am I going to start from? I'm going to start from 0, 4, 8, 12, right? So the logical address, for example, could be 346. That's a small number. And then the relocation register will have this number in it, 14,000. And it's a new plus. So I'm going to get 14,346.
How does that work if the logical address is a really high number that doesn't actually exist, but the MMU is adding, but it's adding to a place that doesn't exist? So what do you do? Because you mentioned before switching to
It
disk.
will have to be subtracted.
But then,
The relocation register will be a negative number. That's all.
but what if it changes? Like
It'll be a negative number.
But what if it varies? Sometimes the logical address is low, sometimes it's high. So how does MMU?
No, because remember, so we're gonna. So let's start off with. You're right. First of all, imagine the program is mostly in one location. It's still giving a block space. So that's why this register is going to be useful. I'm going to always be in a certain range. Now, you're asking is, can it change? Yes, we're going to talk about that. Can it change? And in fact, if you think about it, there's going to have to be a relocation register for every single process. It's not going to be the same between the processes, right? Every process will have its own relocation register. Now, whether there's actually multiple relocation registers or not is a different question. We could, because remember, the CPU is only running one process at a time. So we can say like this, the process control block, the PCB, has in it a new piece of information, the relocation register for that process. And when I do a context switch, right, when I do a context switch and I bring this program into the CPU to be run, I'll also copy its relocation register value into the relocation register of the MMU. It's not the MMU has multiple registers, there's one register. But before I start running a program, I put into that register the correct value
What
for
did
that
you say about
process.
the process control block?
I said process control block is gonna, in addition to all the other things we know it has in it, like all the registers and the stack locations and all those things, it's gonna also have a relocation register value. It has all the, remember it has all the register values. All the 32 registers that we learned in Mips are in the PCB, but it also has the relocation register, which will be loaded into the MMU when the process begins its run or comes back from a switch, from a context switch. Right? It was in a context switch and it came back. So that's the picture here. Wait a second. Now, we didn't do this slide. Here it says that the MS-DOS, on Intel uses 4 relocation registers. I don't know why, who cares, whatever. Theoretically, it could be just 1, right? I don't know why 4. Maybe it saves time if you can keep 4 in memory. You don't have to do. I don't know. You don't have to add that thing. The user program deals with logical address and everything. The physical address execution time binding occurs when reference is made to the location in memory. Execution time binding occurs when reference is made. Right. We talked about this. Execution time binding. That's our whole topic here. Logical address bounding. Fine. So this is not anything we didn't know. I explained to you everything. Relocation register, and like I said, that's associated with the process that's being run.
So the MMU doesn't deal with virtual addresses, like if there's more than we actually have?
No, it could, because the relocation register could be negative. So it could put it, right, it could. Exactly how to do that, that's another topic, that's called virtual memory. I was saying, I was giving a peek ahead. Exactly how that works and how the MMU is involved is not so important. It's basically the same thing, just gonna do a different value. Could be a negative value. Wait, what does he say here? Better memory space utilization, unused routine is never loaded. Why is that?
What does that mean, unused routine?
It means unused function is never loaded. You see, well, he's really throwing in something from later, I believe, because I'll throw it in too. I'll explain to you what he means. What he means is, if we go back to this picture is the most simplistic view. I take the whole process, all of its code, and I put it in memory. But theoretically, we're going to see that let's say that I have fixed size sections. I could have a program that needs 2 sections, and it could be that somebody already using this one. So I could have the process here and here. I could have one process here and here, or even better, I could have one process here and some of its code still on disk. And only when I need the process, I can bring it into the memory and then take a new section. I could have a process, let's say, that takes 2 blocks, and I could 2 of these squares, and I could put in only 1 square. And then when I finally do need the other square, I could then put it in. But in the meantime, I was able to use these for other processes. So that's what he means by saying unused processes, although it's a little bit of anachronism. We're going to get to this. All routines kept on disk in relocatable loader format. Right. In other words, all the functions are on the disk with, where, and they can be relocated. In other words, they can be put in any location. I guess the 4, now I'm thinking about it, I guess the 4 over here, why there are 4 relocation registers, it could be for a particular process, could have 4 different relocation registers. So you could use 4 different sections of memory simultaneously. I guess that's the idea. Anyway, useful when large amounts of codes are needed to handle infrequently used cases. Right. Dynamic relocation using relocation registry. That's the point. In other words, we can have, I didn't make this point clear enough. We can load the whole thing into memory at once, or we can do something called dynamic relocation, where, remind me to read the titles. Dynamic relocation, this is a new topic, using a relocation register. Now, once we have this relocation register, we can now bring in parts of the code whenever we feel like it, and just give a new relocation register, and just say, oh, this card is over there, and this part's over there. When we were when we were doing compile time, we had to know that we had this location available to us. Now we can move things around, so we can do things dynamically.
Wait, so during compile time, we didn't have this?
We didn't have the possibility to do dynamic relocation. No special support for the operating system required. Yeah, not important. Okay.
Can we take a break?
Yes. All right, let's take a break.
Till 1?
Till 1.
I said till when?
I heard 1 also.
Till 11 after. 11.
11:11.
We all should get excited.
11:15.
Let's see where we are. Okay, 11:15.
Oh, you didn't slides. Yeah, I didn't bring my pictures. It just got too heavy. Oh, yeah, injections.
I'm wearing my mask outside just to keep me warm.
Did you see Spider-Man?
No.
No, I was thinking about you. My brother saw it the second time.
Less, they don't build them at all.
And I went, it was so funny, it was on Wednesday night.
Can't.
Yeah, it's so sad. I also got that.
Not actually, kind of, she's like upset, like she's not making noise, and she was like, what? Saying, one of the girls that was there, she was like very, like, teal cats, like she was like, not trying to take any funny business, so she's like, I can't wait.
Because it looks
I don't know
like
what-
It did, it says, no, it says that attach the detailed documents for your use.
And what documents, like, don't worry, like, she was just like, I'm in trouble.
No, I didn't see it, I'm debating,
And they're
I'll tell you what, I
like,
have-
like, what's going on?
I wanna go, because it's like not hype and everything, and I love going with people that like hype and
Yeah,
then like, I wanna watch it with like, I feel like, I don't know, anyone that currently loves Marvel as I do, so my siblings, and currently the only sibling that's actually gonna go to watch it is my brother.
Yeah. And she
Everyone
was
else just,
just
they're not gonna go pay for it, but then, like my brother has kids, and he's got they were like babysitter for it, and like, he's gonna wait for it to come out online, you know? And also my sister, she's pretty much supposed to give birth any day now,
being crazy.
so I'm just saying, like, yeah.
We were like, who is she? Like, how do you?
Long story, I know her due date was the day that when Spider-Man came out, and he like, she's like, the same day, I was like, oh my god, guys, Spider-Man's out, I was like, I'm supposed to be giving birth today, I was like, damn, Spider-Man's crazy.
How do you know that, like,
Yeah,
why
see
she's
commercials
crying?
for everywhere.
Answering your question.
What?
And she was
Commercials were everywhere, like, I used
I
to
was
get
like,
to watch them in the UK, and they're advertising it too, and
her mom and my boss. We were very excited about it.
I haven't seen the other ones, I saw the one, I saw the original and I haven't seen the one that's come out.
Does it suck that you can't talk about it? Like, no, that sounds like a weird
So
question.
it was funny because my daughter whatever watched it.
Okay, so she's
like, so we all talked about it over the weekend.
Never.
Like, also watching it since I was Friday.
Maybe it's okay, maybe
And
it's
then
not.
like I felt like we're not gonna just leave it alone, like.
Okay. View.
don't listen, it's here, listen, you don't really listen. I know.
What about the
That I bought
slideshow?
that was brought to me from the
Right. Okay, so we understood this.
brand that they had like a flavor.
Now this is a sort of a parenthetical topic here, just as long as we're talking about virtual memory and things being outside of on the disk. So there's something called linking. You probably heard the term linking and you don't know what it is.
Like the linker and like when you compile something, so like linker errors.
Yeah, linker error. You don't even know what this linker is. So I don't know 100% either, but I'll tell you like this. What it's basically doing is it's when you do like include something, include some library, the linker is adding your program to your program, another program that you link to, that's linking to. You know, that it's another program that you decide that you need to use for your program to work because you're doing, let's say, you're using some function, let's say rand or some other function that is in some other library. You need to bring in now the code for that. It's not like you magically can run functions that exists in the system libraries. You have to actually incorporate those system libraries into your actual compiled program. And that's the job of the linker, to bring in those other images or those other compiled sources. Or, I don't know, it actually brings the source code and then it compiles it also. So if you link a lot of stuff, if you have a lot of includes in your program, it'll take longer to compile.
If you have a lot of what?
If you have a lot of includes in your program, it'll actually take longer to compile because it's compiling all those things that you include. And that's the job of the linker, to bring those things in. So we say static linking is that the system libraries and program code are combined to make one program by the loader into a single binary program. Dynamic linking is that the linking is postponed until execution time.
Wait, static linking?
Static linking means that I actually bring in those system libraries into my program and compile them all together and make one large compiled program. Dynamic linking means that I don't do that. But yet I can still use the system things. When do I? So I do it at execution time, not at compile time.
Right, so that means, so let's say you included a library because you thought you were going to use something, but you don't end up using it, then it will
Still
never
there.
link it.
Exactly. If you're doing dynamic linking and you included some library, but you never actually called it, it will never actually get brought in. So your code will be small. It'll only link it in when you actually use it.
Which time does this happen?
That's called dynamic linking. That's during the run, during execution time.
So we'll only,
Link, it's all written here on the slide.
I know, but it makes more sense when you say it because it's
Yeah.
like,
I say a full sentence, yeah.
yeah. So
So,
it'll only link it in when it's executing?
yes. Small piece of, there is a small piece of code called a stub. How does this work? And now we're explaining, how does dynamic linking work? There's some kind of stub code, like a small piece of code. In other words, before you actually run your string compare or whatever, your function, your system function, there'll be a little line of code added into your program that'll say, go and fetch this program. So there's that's what we call it a stub. Small piece of code used to locate the appropriate memory resident library routine. Notice what it says. What does that mean, memory resident library routine? It's already in memory. This is also an interesting idea. It could be, let's say you have 3 programs running. It's possible that you could have the same string compare being used by all of them, right? You see what I mean? In other words, let's say I have 6 programs running, they're all using string compare. So each program, if I did static linking, each program would have its own copy of the string compare in it. But I could do it differently. I could say, no, I'm going to load string compare once into memory, and any program that wants to use it will just access that memory resident library routine. It's already in memory. It's sitting in memory, and I know where it's located because I have this stub which tells me where to go find it, and then I can run it, and then I actually save a lot of memory. So I don't have to have multiple copies of the same code.
So it's used to locate memory that's already there?
Of a function that's in memory. Then the stub replaces itself with the address of the routine and executes the routine. In other words, then in your code will be now where to jump to, will be a jump command essentially. Because what is a function? A jump command. It'll be a jump now to the correct location and then jump back. A jump and link, right? Now the operating system will check if this routine is in the process memory address, because the operating system's job is to protect memory, one of its jobs. So maybe you're going outside of your scope. In fact, you probably are. So therefore, it's going to add that location to your legal addresses. If not in address space, add it to the address space. So we're going to have to add that. Like I said, dynamic linking is particularly useful for libraries. System also known as shared libraries. See why it's called shared libraries? Why is it called shared libraries? Because two processes could actually use the same code simultaneously. That's a big finish. Consider applicability to patching system libraries. Right. The problem is versioning may be needed. In other words, it could be that I'm using a newer version of it, or you've got a newer version and I'm using it the old way. We have to make sure that where everybody's using the same version of the system libraries. Otherwise, they could not run the way I expect it. Now we're talking about another topic called swapping. Well, not another topic. This is parenthetical, I think. Wait a second. Yeah, this is a small topic which relates to the idea that, well, I think I have it here. Here, look at this circle point here. Total, this is what I said before. Total physical memory space of processes can exceed the physical memory. So I said that a single process, his memory space could exceed the physical memory. But that's even a bigger finish. But here it's saying a smaller finish, which is that the total physical memory space of all the processes could be larger than the physical memory, right? You could have a gigabyte of memory and you have 3 processes each with a half a gigabyte of need. No problem, because I have a hard drive. Remember I said, this is why we're not talking about really virtual memory. Once we're saying that things are not programs that I want to run are actually on the disk. In other words, I have a compiled version, I'm trying to run it, or I am running it. But in the meantime, when I do my context switch, normally we understood a context switch, right? Normally we understood a context switch as I'm going from one process to another, to another, to another, and then back to the first one. That's context switching, and they're all in memory. But now we can go a step further and say, no, what about this? It could be that the turn of the process that I want to give now to process number 3, but he's not actually resident in memory. He's actually on the disk. So now I'm going to have to do more than just a regular context switch. I'm going to have to do swapping. I'm going to have to bring him in from the disk. Because remember, this only works because we now have runtime binding. We have that MMU. Because we have the MMU, we can put him wherever we want. So we could actually have 2 guys at the same location and swap them back and forth between the disk. So now so back to what I was saying, I have a context switch. It's his turn now, but he's on disk. So I swap him in, swap another process out, put him on the disk, put in make sure the register, the relocation register in the MMU is correct. Start running him.
So the swap is the context switch?
No, so context switching before, we've talked about context switching before.
Right.
Swapping is a new step that we can add to context switching that we didn't have to do before, or we weren't able to do. Now we're able to do it because we have an MMU. We can actually take somebody out of memory. What I was saying is before we had a context switch where everybody was in memory and we just switched between one program and the other, and we didn't really talk about, and we were assuming their compiled time. We were assuming their compiled time address binding. We were assuming we just somehow knew where each one was, and that was it. But now we're talking about the MMU, this execution time
So you can switch
binding.
between the
So I can
disk
actually
and the
take
memory.
somebody out and put them onto disk and put somebody in. So I could have a gigabyte of memory and 3 programs, each with a half a gigabyte need of memory. and no problem, I'll just use my hard drive. So that's what it means backing store. When you see the word backing store, it means hard drive. So a process can be swapped temporarily out of memory into a backing store and then brought back into memory for continued execution. Backing store, fast disk, large enough to accommodate copies of all memory images for all users. Must provide direct access to these memory images, right? Whatever. In other words, a hard drive.
So
Roll in
backing
and roll out.
store is like a hard drive.
Backing store is a general term for things that you can store that are not in memory. It could be a hard drive, it could be a tape drive. Generally, it's a hard drive. It could be a flash drive. Backing store is like the general term. Roll out and roll in. Swapping very used for priority. Right. Okay. So first of all, I said I don't have enough memory. I don't have enough memory to keep everybody in, so I got to use the hard drive. There's another possibility. It could be that I it could be that I have a low priority process that I guess I have to say I don't have space for him, and I put him off on a disk, and I'm going to skip over him. I'm just going to do my context switching among the ones that are higher priority, and I'm going to ignore him. I'll let him sit out, have a rest, because he's a low priority. So that's called roll in and roll out. In other words, swapping very used for priority-based scheduling. Lower priority processes is swapped out so higher priorities can be loaded to execute. In other words, whatever, I don't know why it could be that I load him in and out, it could be I can leave him out, but the point is I can use priority also. I can say, it doesn't have to be round robin, I can have priority and say, sometimes this guy's out.
So what is rollout rolling?
Just means that I use priority when I decide who goes out of the memory. Remember, somebody who's not in memory is going to be slower to run. Like he's going to have to come into memory. And so that's going to take time of transfer. Total transfer time is directly proportional to the amount of memory swapped. If it's a gigabyte program and I'm going to swap him out, it's going to take time to bring him in. My context switch is going to take a lot longer. So it's not really great. It's not really so great. So maybe I will put somebody, I'll keep everybody that's high priority in memory all the time, and some low priority process I'll leave out. System maintains a ready queue of ready to run processes which have memory images on disk. So now we're talking about another ready queue. In other words, this is not the ready queue that we talked about before, it's another ready queue, which is saying people on disk that are happy to come into memory. It's kind of the same principle that we had before. Where before our ready queue was the programs that are interested in getting CPU time. Now these are programs that are interested in getting memory. They want to come back in. Does the swapped out process need to swap back into the same physical address? So not necessarily, right? Remember, I could change we were saying, do I have to come back to where I was? Like I could have process 2, 1, 2, and 3 on the disk. It could be that 2 and 3 keep switching, right? It would work. I would just. Or it could be that sometimes 3 goes to where 1 was, and then 1 goes to where 2 was. Do I keep them? And this is called, what is it? I don't think it's written here. Affinity, called affinity. The term affinity means that we do desire to have them in the same location. We'll talk about, I think we're going to talk about more.
So we're saying you don't want them in?
They don't have to be in this. Theoretically, they don't have to. That's why it's a question. Does this need to be in? Theoretically, it could be in different locations. But there is an idea of called like, that's processor affinity. Processor affinity is when you want to be on the same process. Whatever. There could be a desire to have an affinity for that same location, to keep them in the same location. Let's see. So we asked this as a question. Depends on address binding method. Why? Plus consider pending IO. Yeah, you get into certain complications. What if you try to swap out somebody who was in the middle of waiting for an IO? Remember, he wasn't running. Why wasn't he running? Because he went to IO. We don't always stop somebody because the time slice ended, right? We stop somebody because he went to IO. If he went to IO, he is now waiting for a read. There's stuff being written to a buffer. If you throw him out of disk, where's that IO going to go? It's supposed to go to memory. He's reading from disk into some memory location, and so we swapped him out. Now we're going to put him on disk. Where's that memory going to go? So we have a problem. So actually, I think on the next slide we talk about it. Swapping normally. here, now this talks about like swapping is normally, we actually don't do so much swapping. It used to be swapping was a big thing. I think that it's not so popular anymore because memory is big and the time to copy is too slow. Wait, do I talk about this thing? But wait, I wanted to say. Yeah, double buffering here, the next slide. Here, so here, remember I talked about pending IO? I'll just look here. I went 2 slides ahead. If you do the swap out while there's a pending IO, then when all of a sudden the writing comes, it'll go to the wrong process. It'll go to the wrong place on disk. It'll go to the same place on disk, but it'll be the wrong process. So you could do something which is not so great to solve this problem, which is called double buffering, which is that you make an extra buffer in the operating system, and you say no. If somebody, anytime somebody wants to wait for an IO, it's the operating system will make an array for it and write it into its own array, and then when it gets it all, then it'll give it to that process if the process is in memory is being run. So the operating system will kind of act as a storage location until the process is ready. But this is means you have to do double buffering. You have to copy it from the disk to the IO's own personal array, and then when you start running that process, you're going to copy it from the IO from the operating system into that process. So that's going to be a little bit of another slowdown.
So it only gives, so if the memory, let's say, is ready, but the process is in the IO
Is on
queue,
disk.
it's in the IO section, then it will just, there's just waiting to give the memory to the process that's in IO.
No, you didn't say it right. If the process has been swapped to disk, and yet he was waiting for some IO to occur, so the operating system could store it for him.
Mhm.
It's like if you're in shul and they're throwing candies, so you take some for your kid who's not there. The parent, the IO is like the parent, and he can take care of the process's IO even though he's not on disk right now. And then when he comes back, he'll give it to him.
But one thing, the write only is holding what the IO, like what the user inputted, or not the user, whoever.
So
The array, that buffer array,
yeah.
it's only holding the input, right? It's not the whole process.
No, exactly. It's only the input for the process. This is storing something.
And
When
then
the process eventually comes back to memory, then he'll give him the data.
They don't send the input to
The disk.
No.
Okay, well, that was just to answer. That was just to fill out that slide on. Okay, so here is a graphic representation of what we just said. Notice that you're swapping out a process, swapping in a process from the backing store. Backing stores are always drawn as a cylinder. But that means like a disk. Think of that cylinder as a disk. And that's the memory. Okay. Here, if next process to be put in CPU is not in memory, need to swap out a process. Right, so then according to my ready queue, I'm supposed to do process number 3, but he's not in memory, he's on the disk. Need to swap out a process to make room for him. The context switch time now is all of a sudden going to be very high because we're not just doing our normal copying of registers and letting the next guy run. We're all of a sudden copying data from a disk to memory. That's much slower. So, for example, if you had a 100 megabyte process at a transfer rate of 50 megabytes, the swap out time will be 2,000 milliseconds.
How?
In other words, it's 2 seconds. Because just think about it, it's very simple. It's 2 seconds, right? Because it's 100 megabytes, 50 megabytes a second. So it's going to take you 2 seconds, right? Otherwise known as 2,000 milliseconds. Milliseconds, 1,000 milliseconds. Plus swap in of same size process. Now, to take the guy out will be 2 milliseconds, and take the guy in will be 2 milliseconds. So it's going to take us 4 seconds. It's like 2,000 milliseconds. Can reduce if reduced size of memory swapped by knowing how much memory really being used. It could be that we only put in part of the program, so we could save things. There are some system calls like request memory, release memory. That would mean that the user is, the program itself is swapping itself. And this we talked about, double buffering. Standard swapping is not used in modern operating system, but modified versions swap only when free memory is extremely low. Well, that's what we've always been assuming. We would only swap if the memory was very low. Why would you swap? You could theoretically swap things out, even though you have plenty of memory. Just have a spare memory, maybe. Swapping on mobiles, not typically supported. I don't know. This is from like 2013, so I'm gonna skip this because it's probably whatever it says is probably not true anymore, or might be true anymore. But whatever. The point is, swapping doesn't necessarily. It's not. Don't think that swapping necessarily. Whereas the MMU is definitely definitely being used. Swapping is not necessarily happening nowadays or on all devices. Okay, now we're getting into how much time do we have? When do we finish?
11:45.
11:45. Okay, so we'll start this and we'll continue next time. This is a major topic, and it all relates to this. It relates to what I said before about, how do we locate these things in memory? Wait, where were we? I should sort of give you an overview. There's basically two here. Is this good? Well, I'll just look at this picture I'll use this. This is not exactly showing what I wanted, but I'll just use this picture anyway. Here we have process 5, process 8, and process 2. Notice that they are different sizes. There's basically two schemes for how do you put multiple, we talked about each one is gonna have its own, each one's gonna have its own its own relocation register and MMU. This one will be wherever this value is, this value, and this value. And notice the limit register will be a certain size here, a larger size here. The limit register will be bigger, it's a bigger space, and a smaller, again, smaller here. These are all called contiguous allocation. Contiguous means that all of process 5 is here. And all of process 8 is here. They're contiguous, it's one section. But that's one possibility. The other possibility is you could have non-contiguous. You could have that 5 would be here and here. Because it could be more efficient. Because let's say I had process 1 over here, and he only needed this space. And then process 8 came here. And then 1 left. 1 finished. And now I've got 8 sitting here in the middle, but I got a section here and a section here. Comes along a new process, 9, and he says, I need a bigger space than this. Well, I don't have a bigger space than this because these two are the same size, let's say. But if I can make his allocation non-contiguous, then I have room for him all of a sudden. So it'd be nice to have that flexibility, to be able to take a process and essentially have like 2 relocation registers, think about it, right? He'll start here, but certain addresses after a certain point will jump to here. Here I'll add to them, I don't know, nothing, because this is, let's say, 0. I mean, it's not 0, but here I'll add to them 1,000. And then if they get past 500, so it'd be 1,500, then all of a sudden, if I want to go 501, I'm going to add to it 6,000. And it'll be 6,501, or whatever. It'll be 6,001, let's say. So I can actually have the same process in 2 locations. So that would be called non-contiguous. So let's go back. So just to add this an overview, that there's 2 basic ideas, contiguous and non-contiguous. So let's first talk about contiguous, because that's more simple. So, okay, so first of all, some ground rules. Of course, the main memory must support both. There has to be room in the memory for the operating system in addition to your programs. There's a lot of people don't realize that. Well, you do realize that. Right? The operating system takes up memory. Not just disk space, it certainly takes up disk space, right? But it takes up memory. That's why you need a computer nowadays with 16 or 32 gigabytes of memory, I don't know, whatever, 16 gigabytes of memory you need, because the operating system itself takes up a lot of memory. Forget about disk space, it actually uses the memory because it's large. Limited resource must allocate efficiently. So contiguous allocation is one early method. So it's useful to talk about, even if it's not done anymore, just because it introduces you to the ideas of allocation. Memory, main memory, usually in 2 partitions. In other words, what he's saying here is that the operating system needs to know, it needs to be in a different section from the So I don't think it's really true anymore that main memory is in two partitions, but partitions, I don't like the word partition. But certainly we can say that the operating system shouldn't swap itself out, right? That would be problematic. It can't swap itself out because it can swap part of itself, but it can't swap itself out because it needs to be running all the time. So there's a section, it has to know not to swap this section of memory out. So there's a special section of memory that shouldn't be swapped. That's for the operating system. Resident operating system usually held in low memory with an interrupt vector. Okay, we didn't talk much about the interrupt vector, and I'm not going to talk much about it, but the point is the operating system is usually at the bottom or 0 in that area. User processes are then held in higher memory. Each process contained in a single contiguous section of memory, just like in this picture. Okay. Each relocation registers used to protect process. So we talked about that, relocation registers, and from changing operating system data. And they should be, we also need protection. Protection means that I don't access the values in memory that's not mine. We talked about the so the relocation register is also called the base register. Here he calls it the base register, a bit confusing because he changes terms a lot. But the base register is the smallest physical address that you're allowed to use. The limit register is the range. See, it's not the highest. You would think that it's the base register plus the high. It's not, it's the range. It's how large you can go. Each logical address must be less than, we said that already. MMU maps the logical address dynamically. We already said this. Can then allow actions such as kernel code being transient and kernel changing size. Why is that? The kernel code can. I guess that's the idea that since you have a partition, then the kernel will always be in a certain section. So you can bring him in and out of memory if you want. You could theoretically have parts of the kernel not being run right now. They could be on disk. But you can bring them in, and the kernel could change size because you could change the value of the limit register, and then you can give him more space. Okay. This is pretty much the same thing that we saw before, right? But it's not the same thing. This is the check. You see, here, what we showed with the MMU, here, let's see the difference. With the where's the MMU? With the MMU,
There's no base here.
here's the MMU with the base, and we said if it's greater than the base, we were assuming there's an MMU over here. Then we said it's good, and if it's less than the base, then it's not good. What are we saying over here? Let's see if it's the same. I'm not sure it's the same. Here. Logical address. The CPU creates a logical address. See, now we're showing kind of the hardware support for relocation. We're now showing what the MMU is doing. Right? Here's the plus. The limit register comes in. The logical address needs to be less than the limit register. What does that mean? Remember, the limit register is how big of space am I allowed to have? Am I allowed 1,000 bytes, 2,000 bytes? So this is that number, how big it is. So the logical address is always going to be less than that limit because it's not an absolute limit. It's just the total size that I'm allowed. So it could be 0 is fine, 1 is fine, as long as it's less than the limit. Then if it is less than that limit, then I go ahead and add to it the relocation register. I took that 5 and I added 10 million to it. So that's 10 million and 5. And now I got my physical address.
Could you just repeat that about the limit register?
Yeah, the limit register is like if this block, do we have that picture? If this block over here is 1,000 bytes, the limit register will be 1,000. But the base register is going to be wherever it's starting. Let's say its starting point is at 10 million. So the size of the largest address I can have is 10 million. And I said it's 1,000, so 10 million and 1,000. That would be the largest address. But when I first get the address, the CPU creates a logical address. So that's just like a number like 0 or 100, but it's going to always be less than 1,000. Assuming that picture was 1,000. So as long as it's less, so my living registry will be 1,000. As long as that address is less than 1,000, then I'm good. Otherwise, I have an error. Now I've got that 1,000, but I need to add to it the relocation registry to get to the actual physical location. So that's what I'm doing over here. All right, we'll stop here. We're still talking about contiguous allocation. Oh, no, wrong one. Contiguous allocation. Yeah, we'll talk about that picture. And then we're going to talk about these algorithms. Okay.